So let me continue. So last time I gave a quite concrete definition of the category of Chow motifs. So I wrote a formula for the morphisms between, well, say if X is a smooth projective variety, then we have the motif of X, which is X, comma, the identity morphism, so identity in the category of correspondences. And then I wrote a formula for morphisms in this motivic category between, say, motif of X and motif of some other variety Y, which was like the Chow group of the product. Well, of course, just to bring it into accordance. So before I was talking about general oriented cohomology theory. So here you can put instead of Chow groups any oriented cohomology theory, and even for some applications it is necessarily to do it. Just to put here not Chow but a well, and the definition works exactly in the same way. Well, so the last thing I would like, so the last basic thing I would like to define concretely are Tate motifs. Well, actually, it's good to have a concrete formula, so in coordinates if you want. So there are several ways to do it. So one possible way is as follows. So we take the motif of a projective line. So then, so maybe I should say first in general that for any smooth projective variety X, sometimes we can decompose its motif into a direct sum. So sometimes we can write it like this. So where pi is a projector. So it's an endomorphism of X, or the motif of X, well, which satisfies this usual equation. So then, of course, we can continue to I mean, if possible, to decompose this motif and that motif. So unless we get a complete decomposition, so as a direct sum of indecomposable motifs. And this is the way how we do it. So we take this diagonal morphism and try to write it down as a sum of pairwise orthogonal projectors. Well, and in this sense, so let's plug in P1 here. So the motif of P1. So P1 delta P1. So then we can decompose it, indeed, into a sum of two motifs. So one is denoted by Z and another by Z1. So this will be the Tate motif. Well, with shift 1 if you want. So where? So this one, it's P1 and so let me check. The respective projector looks like 1 times point. So delta, so it's an element in, well, dimension is 1, so Chow 1 of P1 times P1. It has a concrete formula, so there are classes, there are points, and there is P1 itself. So the diagonal looks like 1 times point plus point times 1. And this is exactly the decomposition. So this is P1 point times 1. And this motif is actually isomorphic to the motif of a point. And this is, by definition, the Tate motif. So then we can produce bigger shifts taking the tensor product. So Z shifted by n, it's Z1 tensor n times. Actually, note this shift is not the same as in all previous talks. So actually, this shift in this Z1 is actually Z12. But since so in my lectures the second number is always twice the first number, I will omit it. I mean, usually in the literature you can find notation like this, but these curly brackets, it's not easy for me to draw them, so I prefer round brackets, but it always means, well, actually, shift like this. Okay, so another way to define the state shifts is as follows. So instead of P1, we can take Pn, and then do the same. We'll take the diagonal, so it looks a little bit longer, but it can be explicitly written down. And then just, it turns out that this is Z plus Z1 plus Z2, and so on to the n. So in this way you can, it's another equivalent way to define Tate twists. Also note that if you take the Chow group of Pn, it's the same. It's Z plus Z and so on. Well, n plus 1 times in degrees 0, 1, and so on n. So it's completely compatible. Also, remember, so last time I draw a Hasse diagram. So let's do it again. Well, unfortunately, I don't have place here, but it's n plus 1 points. Well, or if you count from 0, well, it depends how you count. Well, and so let's connect them. So this is the Hasse diagram, which corresponds to the motif of Pn. Well, okay, so it's also convenient, so let me write down some formula. So it's convenient to have a formula how the morphisms of twisted motifs look like. So if you have some motif M, so then we can twist it by some number L, which is by definition M tensor the L. So such twists appear very frequently, so it's practical to have a formula for morphisms between, say, x pi shifted by M, y rho shifted by L. So let's assume that x is irreducible, just to make the formula a little bit smaller. So this is the following thing. Chow lim x plus m minus L x times y rho. Because it's always a difficult decision, should one write plus or minus? Oh yeah, oh yes. So first pi and then rho. Yeah, thank you. But for me, the most difficult decision is to write plus or minus and plus. So I checked it many times. This should be a correct formula. Well, so then, so let's do some computations. So for projective space, it's not so difficult, but let's do a little bit more. So more examples. So there is a theorem of Karpenko, which will help us. So namely, let us consider the following situation. So we have a variety x, which is, say, x0, which is smooth projective. So then assume we have a closed, this is a symbol for a closed subvariety, so x1, then we have a closed subvariety x2 inside of x1. So we have a filtration which ends, well, some point xn, and then let us also put the empty set here and assume that the difference is x0 minus x1, x1 minus x2, well, and so on. So here, well, xn minus the empty set. So are so affine fibrations of ranks R0. Also here, no, R0 is here. Always some smooth projective variety. So this is R1. Also, well, and so on. Also here, so I omit the difference. So Y2, R2, and here Rn, Yn. So again, all these are the rank Ri affine fibrations over some smooth projective varieties Yi. So then there is a concrete formula for the motive of X, which looks as follows. The motive of X is a direct sum of the motives of this basis, well, from 0 to n, shifted by these ranks Ri. Just compare this formula with the analogous formula for the Chow group of X. So the Chow group of X is a direct sum of the Chow groups of Yi shifted with minus Ri. Of course, this formula is stronger, because I mean, this is formal consequence of this when you take realizations. So now let's consider some examples. So we will be mainly interested in quadrics for the applications, but let's start again with the projective space. Just get the same result again using this theorem. Well, it's not so easy. Okay, so examples. So the motive of projective space revisited. So let's take the following very short filtration. Just take a hyperplane inside of Pn and so the empty space. Just very short filtration. So actually it's called relative cellular filtration. Well, so what are the differences? I mean, the difference here, it's rank 0 fibration over Pn minus 1, and the difference here is just the affine space of dimension n, so it's rank n trivial, well, affine bundle, vector bundle over a point. So it means, so it follows the motive of Pn is just the motive of a point, which we denoted by z here. So z is the motive. But now shifted by n plus the motive of Pn minus 1, and you can continue inductively with shift 0. So we don't write shift 0. Well, so at least it looks good. Yeah, sure. Yeah, absolutely. Yeah. So let's do it for quadrics. Well, so this is an example which appears in a paper of Markus Rost. let's take the following smooth projective quadric. Just concrete equation. So in projective coordinates, well, so we take n+1 dimensional projective space and quadric given by the following quadratic equation. Plus qx2 n+1. So I want it to be n-dimensional. So therefore, so I take here n+1 to make the dimension n at the end. Okay, so let's consider the following filtration of Q. So Q, it will be, well, x0. So then we take the following subvariety. So subvariety given by a simple equation x0 is 0. Note that I said that y's are smooth and projective, and I did not say anything about x, xe. They are usually not smooth, but it's okay. So in this case, it's not smooth, this subvariety. So y should be smooth, but not axis. Well, then inside of this, we take a point, namely the point 0, 1, 0, 0, 0. Well, and finally we take the empty set. So now let's look at the differences. Well, so I mean here it's easy. So this is rank 0, a fine bundle over point. So this is x1. Oh, this is x2. Well, so what is the difference? Well, it's very easy exercise. Yeah. The difference is, yeah. The difference, yeah. Well, okay, so let's, I mean, actually it's a very interesting exercise, so I mean, everyone can do it, but I like to do it by myself now, because it will be exactly what we want. Just, well, so what is, so let's start here, x1 minus x2. So x1 minus x2, which is the same as, so x1 minus this concrete point. Well, so there is the following obvious projection to q prime, so it's which is quadric given by the equation q is 0, smaller quadric. Just an obvious projection when the point x0, x1, xn goes to, I mean, we forget the first two coordinates, simply. So x2, so xn plus 1, xn plus 1. Well, it is well defined because the only problem which can appear when all coordinates here are zeros, but if all these coordinates are zeros, then, well, x0 is 0 anyway, then x1 should not be 0, but we removed this point. So it's well defined. Exact, I mean, it fits exactly. So we need to remove x2. So what is fiber of this projection? Well, it's really an easy computation. So if we fix this point, then well, x0 is actually, well, as I said, x0 is always 0 because we are on x1. Well, x1 can be arbitrary, so the fiber is a1. It's a fine line. I mean, just so we have here rank 1. So So it was X, so it was here. So here we get rank 1 bundle over Q prime, over smaller quadric. So now, I mean, the last missing point, x0 minus x1. Well, actually, in the theorem of Karpenko, it's about vibrations. So just the fibers should be. So it shouldn't. So I say bundle, but I don't. Exactly. I mean, the theorem of Karpenko is quite strong. But I guess in this case it will be even bundle. But we don't care because of. Well, so x0 minus x1. Well, or q minus x1 if you want. So let's write explicitly what does it, I mean, these are points on the quadric such that x0 is not 0 this time. Well, if x0 is not 0, we can divide by x0. So it's isomorphic, so namely divide by x0 to so now we have affine coordinates, but we should not forget that we are on a quadric, so it should be plus some equation, but the equation is, so dividing by x0 means putting 1 instead of x0, so it's y1 plus q of y2 yn plus 1 0. And so they are y2 up to yn plus 1 are arbitrary. Y1 can be found from this equation. So this is isomorphic to an. So just n arbitrary parameters. So here it means rank n vibration over a point. So, and it follows that the motive of this Q is, well, let's do it from the right. So Z plus the motive of Q prime shifted by 1 plus the motive, the Tate motive shifted by n. Such a formula. If you want, again, we can go inductively for Q prime, we can do the same for Q prime, provided we can present Q prime in this form. Just to, I mean, we need this x0 times x1 at the beginning to proceed. I mean, if you can do the same for Q prime, we can go on. Well, so this is a famous formula of Rost. He used it in the construction of Rost motifs. Well, and the last but very short example. So let's take a hyperbolic quadric. So, which means a quadric satisfying the following equation. Let's call it. Well, and this quadric has the following, so very short filtration. So Q and x1, which is, so we put all x coordinates to be 0 and the empty set. So then, well, if all these coordinates are 0, then there is no equation. So the equation is automatically satisfied. So this variety is just isomorphic to to the projective space PD. Well, so rank 0 vibration over PD, so it's easy. And here there is again an obvious projection again to PD. So when we put a point on a quadric, so here x0 yd. So then we forget y's. So now, well, again, since not all of them are 0, this is well defined. So what is a fiber? So a fiber, so the x's are fixed, and here we have a linear equation when x's are fixed. So we have just d parameters, arbitrary d parameters y. So it's in a fine space AD. And at the answer we get that the motive of Q is the motive of the projective space plus the motive of the projective space shifted by D. So yeah, and for the motive of the projective space, you again take the previous formula and plug in. So at this point, let me draw the Hasse diagrams for quadrics, because so here it's the even dimensional case. So there are even number of variables. In this case, the Hasse diagram for the motive looks well, just like this. So here in the middle dimension, there are two Tate motives. So we can connect. So it looks like this. So we start from 0, 0, 1, and the dimension of Q is 2D. So this is the vertex number 2D. So 2D, 2D minus 1. So here in the middle, I guess it's D. And there are two Tate motives in the middle. So one coming from here and one coming from, you see, there are two. One from, it's ZD 2 times. So one coming from this and one coming from this. So if you want, this is the first one or the second one, and this is another copy of PD shifted by D. Okay, so we shift it to the right. Well, so this is the even dimensional case. So, and also we will need the Hasse diagram for the odd dimensional case. For this, let us use the previous formula, this one. Let us proceed by induction, assuming that Q is a split quadric. So it's a quadric of a maximal width index. Well, so if Q is split odd dimensional, also then so the Hasse diagram looks as follows. Well, we just continue to split Tate motives from both sides. when the dimension of Q prime becomes less and less, at some point it will become, so it can't become 0 because it's odd, so it will become 1. It should be odd. So at the end, we have one-dimensional quadratic, and the next step, it disappears. So we have the same answer as for the projective space. So we have a chain. Well, here is the middle, so now it's between two vertices. So 0, 1, and this is dimension of Q, which is odd. Well, actually, this is indeed true. The motive of a split odd-dimensional quadratic is isomorphic to the motive of the projective space of this dimension. So there is this difference between even-dimensional and odd-dimensional, and so one should actually care about it in computations. So there are more examples how you can, so one can apply Karpenko's theorem. So let me mention so Breuer decomposition. So this, yeah, so it works. So it should be example number 4. So Breuer decomposition. Of G modulo P. So G is again split semi-simple algebraic group. So P is some parabolic subgroup. So then just the motive is a direct sum of Tate motives in an explicit way. So the shifts are known, and one can also draw respective Hasse diagrams. And so slightly more general, we can take a smooth projective variety. Well, so again, everything is over some field K, and assume that X is equipped with the action of Gm. So Gm acts on X with a finite number of fixed points. So then again, the motive of X can be, well, so it depends on action, but can be explicitly determined. So it's again a sum of Tate motives. Well, so the shifts, it's a little bit more trickier. So it really depends on the action, but it can be, well, I mean, there is a way to determine. So this is a generalization of the fourth example, because here there is indeed an action of Gm with a finite number of, so it's a strict generalization of the example with G mod P. Well, so I think this is all what I wanted to say about Chow motives and so the examples. And let us go to the second part, so a crash course on quadratic forms, like 20 minutes, just to fix some definitions. Just very few definitions, but quadratic forms. So we need some terminology. So the next part will be applications. Well, first, to avoid any kind of problems, let us assume that our base field has characteristic different from 2 globally. So and Q, so let Q denote a quadratic form over K. Well, which is just in the usual sense, like some quadratic map from some vector space to K. Also assume, to avoid any kind of problems, that it's non-degenerate. As always, so all quadratic form. I should have said here. So, of course, in all examples before, all quadratic forms. Otherwise they're not smooth, and it's not so clear anymore. So non-degenerate quadratic forms. So then we will need so the first basic invariant. It's the width index of Q, the classical one, which is the maximal, the dimension of a maximal isotropic subspace. But I would like to take a different but equivalent definition. So namely, so it's maximum dimension of totally isotropic subspace of V, so vector space where the quadratic form lives, but it's more convenient for us, because of motives, to say in a different, equivalent way. So we can write Q as follows. We can split off, some number of hyperbolic planes, namely as many pieces as the width index of Q is, plus so what is called the anisotropic part of Q. So this is some anisotropic quadratic form. So where H, the hyperbolic plane, is just so it's the basic result that each quadratic form can be diagonalized. So this is the form, so two-dimensional form which has 1 and minus 1 in the diagonalization. Okay. So
Q anisotropic. What does it mean?
It's the rest. It's what remains. So we split off the hyperbolic planes. So actually, equality always means an isomorphism. So we split off as far as we can go, and what remains we denoted by Q anisotropic, and this is a quadratic form which is anisotropic.
Yes.
I mean, in the usual sense.
So it means that it has no non-trivial zeros.
Exactly. So the respective quadric, projective quadric, has no rational points. And just all this is equivalent. And so the number of hyperbolic planes which we can split is exactly this number. It can be 0. If our quadratic form was anisotropic from the very beginning, then we can't split anything. So the width index is maybe 0. Actually, it's usually 0. But then we can define the higher versions of the width index, namely as follows. So I think it's not so well known. So the higher width indices. For this, we need first of all the function fields of quadratic forms. So function field of Q. Well, this is the same as the function field of the respective projective quadring. Q equals 0. So let's denote it by capital Q. So here one should be a little bit careful in the two-dimensional case because, well, so maybe a small remark. So it can, well, actually, for us, it's not a problem because dimension is usually big. But formula, so in the two-dimensional case, there is one exception. So namely, well, actually, maybe just in general, the function field does not depend on the scalar. So we can, so if you take a proportional quadratic form, the function field will be the same. So we can always normalize a quadratic form as we wish. So therefore, we can take the following binary quadratic form, so with coefficients 1 and minus a in the diagonalization. Again, just completely in general, so the notation is k of q. Just completely in general, k of alpha times q is the same as the function field of q for all invertible alphas and for all quadratic forms. So the function field in this two-dimensional case, well, sometimes it's what we expect, so k with the square root of a, but sometimes it's k times k, so depending whether a is a square or not. A is not a square, and here it is a square. But it's the only exception, so it's that it's not a field. So it's called function field, but it's not a field. But it's the only case in dimension 2. So it's okay. So now, so a trivial or almost trivial remark: if you take any quadratic form and extend our scalars to the function field of it, this quadratic form is always isotropic. So it has a non-trivial 0 over its function field. The generic point, if you want. And this motivates to give the following definition of higher width indices of Q. Well, so we start with the zeroth higher width index. It will be the old width index, not just the usual width index of Q. But then the first higher width index, so this is already quite interesting. So I1, so we define it as follows. We take the anisotropic part of Q from that decomposition on the right. So it's anisotropic, and we pass to the function field of this anisotropic form. This form, by this remark, is isotropic, and we can again take the width index, the usual width index of it, and we denote it by I1, by definition. It's the first width index of Q. And we can continue. So we continue. So what is I2? So we can. So one can give a recursive definition. Well, so if we denote all these by Q1, so then we take Q1 anisotropic. So the anisotropic part. So again, it's according to that formula. and pass to its function field. But I mean, it's already over this field, so it's function field of so it's called function field of Q1 anisotropic, and again take the usual width index. So these numbers will become smaller and smaller and smaller. So it's a finite process just because of this remark that on each step we split at least one hyperbolic plane. So the width indexes each time is at least one. So the process is finite. Well, and so on. And this sequence, I0, I1, I2, and so on, is called the set. Well, it's not. It's ordered. The higher width indices of Q. Well, so there is a remarkable result of Knebusch about them. So namely, that for any field extension of our base field, finite or infinite doesn't matter, arbitrary field extension, if we want to compute the width index of Q over this bigger field, it's one of these numbers. I mean, not quite, because I mean it's a tricky reduction. So is one of the numbers I0, I0 plus 1 plus I1, I0 plus I1 plus I2, and so on, because it's relative. I mean, because each time we take the anisotropic path. So there are just finitely many possibilities, and they're actually restrictive. I mean, it's, well.
Could you also define the inductive process of defining higher frequencies? Every time you have to split off as many hyperbolic planes as you can. Could you also not do that? And then say from the hyperbolic plane, you do something like a rational fully transcendental extension, and then do something like Winger's theorem that you cannot have something more isotropic planes on the rational field extensions than you had before?
You mean how to prove it? Or?
No, I mean for an alternative definition of higher frequency, you could just take all the hyperbolic planes with you and then...
well, if there is at least one hyperbolic plane, the function field is purely transcendental. So then one should take something else instead of function. I mean, if it's purely transcendental, then nothing changes.
Exactly. That's why I thought it could also be possible to make these definitions without...
You mean without this deep recursion? Or... Well, we will not need this, but it's just remarkable that instead of taking all possible field extensions to determine all possible higher width, it's sufficient to take just this finite number of function fields. Well, so now, of course, we will need the Pfister forms. Well, so everyone knows, but it's just one line. Just to fix the notation. Well, I as invertible scalars. Well, for instance, if n is 1, so it's this form. If n is 2, then it's, well, maybe let me do it. So one computation. So this form, so it's the norm form on a quaternion algebra. Quaternion algebra AB, and threefold Pfister form is a norm form on an octonion algebra. ABC. Well, also we will need the Witt ring of K. Well, which is again just one line to define it. The Grothendieck group of isometry classes. Well, of non-degenerate quadratic forms over K modular hyperbolic planes. Well, the ideal generated by hyperbolic planes. Well, and here there is a special ideal, the fundamental ideal, we will need it. So which is just the kernel of the dimension. The dimension map from this Witt ring to Z mod 2, so it's modular dimension modular 2, so quadratic form goes to its dimension modular 2. So in other words, this is the ideal which consists of even dimensional quadratic forms. Well, and so I think I think it's the last, or almost the last thing. I mean, in this crash course on quadratic forms. I mean, you know, now the theory of quadratic forms is complete almost. And just the last thing is we need a relation between Pfister forms and the Witt ring, which is also very well known. But just again one line. It's not much work to mention it. Also, one of the basic questions in the theory of quadratic forms is to somehow describe the powers of the fundamental ideal. For instance, I mean, the Milnor conjectures, well, there are two and they are proven, but these are in particular conjectures about the structure of factors. So namely, well, that we have, so we have the Milnor K theory, modular 2, we have Galois homology. Well, and we have also these factors, this graded Witt ring, and the Milnor conjecture says all these is the same, all they are isomorphic. So here, this is an isomorphism. So this is an isomorphism, and here the map is precisely sending a generator to this Pfister form. So I mean, this is the relation. I mean, this is one of the reasons I will need it in the subsequent lectures. Well, so I think this is due to Voevodsky, and this is due to Orlov-Vishek-Voevodsky. So it's, I mean, this was proven later, a bit later. Okay, so I think that's all about quadratic forms. Yeah, and now we can, so now we will combine part 1 and part 2. So the first, I mean, not applications, let's do some computations as a preparation, so namely motives of quadrics. And of anisotropic quadrics. Well, so remember the example of Rost I gave you in the beginning. If your quadric is isotropic, if you can split this summand x0 times x1, it's the same as to split a hyperbolic plane, then we can always reduce to a subquadric Q prime. So actually the most tricky case is the anisotropic case. I mean, so far I did not mention anything about the structure of motives of anisotropic varieties. So let's do some first example. So there are 5 minutes, and now we will combine the higher width indices with the Hasse diagrams I mentioned, and say something about the motives. So it's called, this technique is called shells. So it's due to Vishek. So namely, we should distinguish even and odd dimensional quadrics a little bit, because the Hasse diagrams look slightly different, like this in the even dimension, and like this, like a chain in the odd dimension. So there is some small difference here. And so let's draw these pictures, I mean, depending on the parity of the dimension, and let us subdivide it. So let's, I mean, here's the middle. Let us subdivide this picture into what is called shells as follows. Well, first of all, assume that our quadric was anisotropic, so there is no, I mean, the width index is 0. So let's start with the first width index, and let us, well, so let me write some. So we subdivide so the above diagrams as follows. So we draw, well, we can, well, I0 vertices, so I1 vertices, so I2 vertices. So we just count. Well, I0 is 0. So we assumed the quadratic form is anisotropic. So let us count I1 vertices from the left. Well, so for instance, like this. So I1 vertices, well, in this example, in this picture, 2. And let's do the same on the right, symmetrically also. So then, so there are vertices here. So let's count I2 of them. Well, so I2. And do the same on the right. Well, if I2 is 1, it's 1. If it's 3, then it's... I will give more concrete examples later. And so on. At the very end, just by trivial dimensional reasons, we will end up exactly, I mean, we will subdivide everything. Because, so one should be a little bit careful here, because here in the middle there are 2 vertices. Well, let's somehow draw a line like this, just to split them, because of this symmetry. So we have a subdivision of Tate motives into some groups, which are called shells. So this is shell number 1, shell number 2, and so on. This is also shell number 1, shell number 2, and so on. And well, let me give you. There is a result of Vyshek. So let me give you first so maybe a more concrete picture, a more concrete example. Well, and so as a next step, we will apply this. Well, so first I will explain it in general, and then we will apply it to Pfister quadrics. It will somehow be very strange. Well, so for example, if you have a picture like this, well, shell number 1, shell number 2, shell number 2, shell number 1. So this corresponds to, so this is I1, this is I2. Yeah, or if you want some bigger picture, well, like this. So it should be symmetric. So shell number 1, shell number 2, shell number 2, shell number 1. So this corresponds to 1, 2. This is I1, this is I2. Okay, so is it clear how we subdivide this? So points, remind you, correspond to Tate motifs. Well, and then there is a result of Vyshek, which, oh, but the time is over. Well, so I will stop here. So there is a result of Vyshek which allows to, so I will tell it next time, which connects these higher width indices, in shells, with the motifs. But, so I will tell combinatorially. It's combinatoric. But I will tell this next time. Yeah, so thank you for your attention.
Questions or comments?
So about the width index number width 2. Is it true that width 2 is the first width index of Q1?
Yeah,
So,
of Q1, or which is over, yeah, but yeah, which is already over some function field of Q.
With R is width index
Of the previous.
of the previous one.
Yeah.
Other questions? Just thank the lecturer again.